Hello everyone, my name is Gagandeep Kaur and today we are going to start our lecture series on quantum mechanics, and this is the first lecture of our lecture series. And this lecture is by Udaan Institute Bathinda, and we are going to talk about some important topics of quantum physics which will help you in your CSIR, GATE and other examinations. So for starting, we will start our lecture series with some basic terminology that is used in quantum mechanics. And first of all, we will talk about the wave function. So as you all know, in quantum mechanics we discuss about an wave-like behavior of any particle. So in that scenario we'll be discussing wave function. So here as we know, the very definition of wave function is that a mathematical quantity that explain about the time related all variables of a particle. So quantum mechanically, a wave function is nothing, a variable quantity that mathematically describe wave characteristics of a particle. So first of all, we will be discussing about the probability of a particle. So what is the probability? Probability is nothing just we are conducting an experiment and we are trying to find whether or not we will be able to find that particle in that given space. So mathematically, if I am going to write the probability of a particle, it is going to from -a to +a psi star, which is a function of x, and psi, which is a function of x again, dx. Here x describes the position of our particle, and from -a to a are the limits within which we are trying to find a particle. Again, so normalization of the wave function. In initial experiment, we were discussing about the probability of finding a particle in a given region. Now we are trying to find that probability from -infinity to infinity. That means in overall space, we are trying to find the probability of a particle. So as we know, if we are conducting an experiment and we are taking limits throughout the space, that means the total probability of finding that particle from -infinity to infinity will be 1, and this is a very condition for normalization of that particle. So psi star x into psi x dx is equals to 1. So this is what we are going to use in future in order to normalize a given wave function. So here we are having two wave functions, psi of x which is less than 0 and greater than 0, and we are supposed to normalize this wave function. So in order to solve different numericals in your quantum examination, quantum physics examination, you are supposed to find the normalized constant of a particle. So here we are going to find out. First of all, we'll put the formula from -infinity to infinity, psi star x and psi as a function of x into dx is equals to 1. So now we are trying to change this formula according to our requirement. As it is given, for x less than 0, wave function is this. So I am going to break this whole integration into two parts, from -infinity to 0, that means function which is less than 0, with our wave function psi star x psi x into dx plus again from x greater than 0, that means 0 to infinity, from 0 to infinity it is again psi star x psi x into dx. So this is how we are going to separate our total probability which is equals to 1. So, for putting the values, so here we from minus infinity to 0, psi star is n e raised to power ax psi star, again psi n e raised to power ax into dx. Now from 0 to infinity, it is from 0 to infinity n e raised to power minus of ax, this is our psi star, again n e raised to power minus ax into dx. So, after this step we are going to integrate this function. So, what we get here is n square, we take it out of the integration because it is a constant, from minus infinity to 0 e raised to power 2ax in dx plus again n square integration from 0 to infinity e raised to power minus 2ax dx equal to 1. So, take n square constant and integrate. After integrating these two functions, we will get n square e raised to power 2ax upon 2a, and limits are from minus infinity to 0 plus e raised to power minus 2ax upon 2a, limits is from 0 to infinity. So, here we took n square common in from both equations, which is equal to 1. So, after this we will put the values. After putting the values, e raised to power 0, that means 1, e raised to power 0 upon 2a minus e raised to power minus infinity n square common plus e raised to power minus infinity minus, here is minus 2a, minus infinity e raised to power 0 divided by minus 2a equal to 1. So, we'll again, as we know, e raised to power 0 is equals to 1 and e raised to power minus infinity equal to 0. So, we'll put both these values in this equation and try to find the value of n square. So, this is 1 upon 2a. Here it is e raised to power minus 0, that means 1. Here it is a symbol of minus and here it is a sign of minus. So, it's going to be 1 upon 2a of the sign positive in n square equals to 1. Okay, so 1 upon 2a plus 1 upon 2a, that means n square upon a is equals to 1, where n is equals to under root of a. So we find this value of n, which is equals to under root of a. This is how we are going to normalize our functions in quantum physics, which will be helpful for you for your numericals. Now let's move to the next part. Now we are going to discuss terminologies in quantum mechanics. First the orthogonal function, and second orthonormal condition. Okay, so orthogonality of function, it is just that if a particle is present in one state, it cannot be in another state simultaneously. So we are going to find the orthogonality of a wave function, right? If a particle, orthogonal means overlap integral between two functions is 0. In other words, if I am taking integration of a particle from minus infinity to infinity in two states, first state is psi n x, here another state is psi m x. That means the integration over these different quantities will be 0. That means if a particle is present in energy eigenstate 1, it cannot be in 0 at the same time. So this is known as the orthogonality of a wave function. Now what is orthonormal condition? It is simple. Similar like this, if you are taking integration from minus infinity to infinity of psi of n of x and psi of m of x into dx, so it is equals to delta m n. As we all know the properties of delta function, if m is equals to n, that means delta mn is 1, and if m is not equals to n, in that case delta mn will be 0. That means particle cannot be in two states at one time. Next, we will talk about operators. So what are operators? Operators are nothing. These are just mathematical functions that we implement in order to find different values. Those values can be your energy eigenvalues. Those values can be your momentum values. For example, in mathematics, under root, if I am trying to find the under root of 9, I will be right under root of 9 is equals to 3 into 3. That means it is 3. So under root is an operator that I am trying to implement on 9. Similar thing happens with quantum operators. An operator works on an observable. Here observable is a function of x. That means we are trying to find something in position coordinates. So when an operator works on an observable, then we will get an eigenvalues time eigenfunction. As you can observe here, eigenfunction and observable are the same. When these two values are equal, that means the third quantity that we get is our eigenvalue. Okay, so let's move to the next part. Here we have an operator, x plus g upon dx has an eigenvalue a. Find the corresponding wave function. We are supposed to find wave function in this particular case. As from the previous slide, we can observe the relationship. A operates an operator working on an observable is equals to eigenvalue times eigenfunction. So now let psi x is your wave function. I am writing it WF. So as I am operating this, x plus d upon dx working on psi of x is equals to eigenvalues. Here A is our eigenvalue. So I am going to write eigenvalue time psi of x, Ax. So x here, x psi of x plus d psi x upon dx. We can take its derivative because psi is a function of x. Now is equals to A times psi of x. Now we are going to rearrange this equation. So d psi, I am just writing is psi instead of psi as a function of x, as we know psi is a function of x. D psi upon dx is equals to A minus x times psi x. Further rearranging it. So we get d psi over psi is equals to A minus x dx. Now what we are going to do next? As always, integrate it. Integrating d psi over psi is equals to A minus x dx. So 1 upon psi, that means natural log of psi is equals to Ax minus x square divided by 2. Okay, so we will get psi x is equals to e raised to power, psi of x from here, natural log will go this side and it will become an exponential, and we will have psi x is equals to exponential e raised to power Ax minus x square by 2. So here, as we can observe, psi x is a wave function of x and its value is this. And this was the question that was asked. Operator has this eigenvalue, find the corresponding wave function. Okay, let's move to the next part. Here we are having this operator del square upon del x square. So from this very operator we are clear that we are supposed to take double derivative of any eigenfunction that is given to us, and we need to find the value of b and also the eigenvalue. So this is our eigenfunction. So as we know from the previous slide that an operator, say A is my operator, when it is working, that means it gives me eigenvalue time eigenfunction. So let's separate it. Del square upon del x square minus bx square is operating. So first of all, let's deal with our derivative part, as it is the double derivative of this function. First we will take the single derivative, del upon del x of e raised to power minus ax square So after differentiating it, as we know, it will be minus 2ax into e raised to power minus ax square. Again we need to differentiate it for second derivative, and I will write it like this. Sorry. So del by del x into del by del x. So we just broke a double derivative into two single derivatives. So we took the first part and now we are going to deal with the second one. So del by del x of 2ax in e raised to power minus ax square. Okay. First of all, we are going to deal with the first part of the equation as we 2ax. So derivative of x is 1. So it is minus 2a e raised to power minus ax square. Okay. So with the second part, minus 2ax into minus of 2ax in e raised to power minus ax square. So this is minus of 2ax square minus of plus 4a square x square x square into e raised to power minus ax square. So this is the value of double derivative. Now we are going to put this value over here. So our original equation was what? Our original equation was del square upon del x square minus bx square, which is operating on e raised to power minus ax square, right? So again we are going to put this value over there like this, minus of 2a plus 4a square x square minus bx square into e raised to power minus ax square. Again here, as we know that any eigenvalue of a function cannot depend upon x, that means this part must be equated to 0. So what we get now is 4a square x square minus bx square is equals to 0. From this equation we can find the value of b. So here our b is equals to 4a square, right? So we can find the value of b, and now we are going to put the whole value of b is equals to 4a square. As we get the value of b is equals to 4a square, and now we are going to replace this in our original equation. So here 4a square x square minus 2a and b is 4a square x square. Okay, these two equations will cancel out and we will get the eigenvalue 2a. So eigenvalue times eigenfunction. Okay, this is a list of some observable and operators that we are going to use in our next lectures, and tomorrow we are going to discuss Schrodinger equation. Before that, you should have a look on all these operators, and from these I would say that momentum operator is pretty important because we are going to use its value so many times throughout our lecture series. So try to have a look on these. Thank you.